All right, so in this video, we are going to be deriving from first principles the C5v character table. And so the first thing that we always do when we derive the character tables is we try to come up with an example molecule to help us visualize things as we're working through this. This isn't a very common point group, and so that's a little harder to do this. It's not as instructive. If you're familiar with the CNV point groups, we know that the most common structures are just prisms. So C3v, it's good to think about a triangular prism, C4v, square prism, and so we're at C5v. This is going to be a pentagonal prism. That's pretty easy to visualize. If you look up, there is a molecule, one molecule. There's a few examples of these sorts of molecules that have C5v symmetry. This is a case where you have a pentamethyl cyclopentadienyl ligand, we call it CP star, coordinating to nickel, and then NO ligand on the other side. That gives you that pentagonal bipyramidal shape. But we can also just kind of draw a generic pentagonal prism. So we draw a pentagon, and then we're going to have an apex of the pentagon. And so, this general shape of a pentagonal pyramid, that's going to have C5v symmetry. So for visualization purposes, and there would be usually a central atom inside there, or in this case, inside actually there, right, floating in between. But you get the idea. This will help us visualize things. So after we figure out, we draw a three-dimensional representation of a molecule in the symmetry, then we're going to go ahead and figure out all the symmetry operations. Well, we always have identity, and we know that identity is always going to be in a class of its own. We also are going to have a C5. And so the C5 is going to be the principal rotation axis that's going through the center of the pentagon and the apex of the pyramid. And so that's doing a C5 once. We're also going to have being able to do that. So that's going to be what, a 72-degree rotation. We can also do a C5 twice. That's a separate operation. We can also do a C5 3 times, and we can do a C5 4 times. And by the time we get to a C5 5 times, that is going to be doing 5 72-degree rotations. That's the same as doing identity, which is just multiplying by 1. A 360-degree rotation doesn't do anything to the atoms. So those are 5 rotations that exist in the molecule. And so let's keep going. And the only other symmetry operations we have here are actually vertical mirror planes. They're vertical mirror planes and not horizontal or dihedral mirror planes, because they contain the principal rotation axis of C5. So there's 5 of them, but they all are very similar. And they all cut through one of these, in this case, methyl ligands, one of the sides of the pyramid, and they cut through the apex. So I could draw it like that. It's going to be a little bit harder to see on this mode, but draw it like this. And what this is going to do, it's going to take this atom and exchange it, these atoms, and exchange them. So those atoms are looking at themselves in the mirror, and in blue here, these are the atoms that are in the mirror plane, so they're not going to change. So here, here, and then if we have a central atom as well. So there's going to be 5 of those, because there's 5 sides of the pyramid, of the pentagon, and so we're going to have 5 different mirror planes. We could write those as sigma v. I'm using hat notation here. Hat notation just means it's an operation to distinguish it from classes. And then we could call the other four, they're also sigma v. We could add primes, right? So we'll have up to sigma v quadruple prime. So now it's time to group all of these into classes. And so the identity operation is always unique. It goes into its own class. So in red here, we'll draw the classes. Identity and inversion always go into their own class. We don't have inversion in this point group. And then we have to think about this, the C's, the C5s. It's tempting to group all of these into the same class, but we actually have to be a little careful here and think about this. And so the way to think about this, there is a mathematically rigorous definition. Basically, it has to do with how you define your X and Y axes, and does it matter? And can you interconvert from one axis system to the other with some other symmetry operation in the group? If you can do that, then they're in the same class. If you can't, then they go into different classes. And I'll have videos on that in the future, going into big detail about how that all works if you want a mathematical proof. But the way to think about this, just without any sort of rigorous proofs, is to think about, okay, what happens to each of the atoms when we do those rotations. When we do a C5, if we define the rotation as going this way, a C5 would go there. If we find the rotation, this methyl group would go there, or this, more rigorously, this atom would go there. And if we do a C5, we define it as going the other way, it's going to go there. And so that sort of depends on how we define it, right? And of course, this atom goes here on a C5, this atom goes there on C5, all of them shift over 72 degrees. A C5 4 times is the same thing as doing a C5, what we call -1 as a notation you could use, just going the opposite direction. And so in that way, depending on how you define things, a C5 4 times is the same thing, spinning this atom all the way around 4 times, all the way around to here. God is the same as if you just define the C5 the other way. So in that way, C5 and C5-4, those two operations essentially are doing the same thing depending upon how you define which way you're rotating. So that is the key clue that tells us that actually C5 and C5 4 times go in the same class. We're going to call that class 2C5. We drop the hat notation here. Sorry, I should have dropped the hat notation there. We're no longer talking about operations. Now we're talking about a class that contains 2 C5s in it. And a very similar thing, very analogous, is going to happen for the C5 twice and the C5 3 times. So we're going to put those in the same class, and we'll call that the 2C5-2 class. Again, depending upon how you define things here, a C5 twice, if we define it as going in this way, would spin this methyl group to here. But if we define the C5 3 times as going in the other way, we go 1, 2, 3, and we get to the same point. So that's why those belong in the same class. All right, so that's the hard part in terms of grouping these into the same classes. The sigma v's, they're all going to be in the same class because they all essentially do the same thing, just different methyl groups. They all bisect through one side of the pyramid, the pentagon, and they contain the apex. So they're never going to change the central atom or this NO ligand, but they are going to move and interswap the two methyl groups or two sets of methyl groups that don't contain the plane. Okay, so now we have those grouped into classes. And so I'm going to now now we're ready to write sort of our bones, so that now that we have our classes, we have 4 classes. We can write our bones of our character table with 4 classes. And we have a total of 10 symmetry operations, right? That's the order of our point group is 10. 1 plus 2 plus 2 plus 5 is 10. So let's go and clean some space up and now start to write our character table. And so we have identity on the top left. By convention, we write the point group of the character table. And we're going to have identity. We're going to have our 2C5 class. We're going to have our 2C5 squared class. And lastly, we have our 5 sigma v class. And over here, I'll leave rooms for functions that we might want to evaluate. So it doesn't really matter what order you put these columns. This is just what, conventions, usually people always will put identity first, and then the principal rotation axis, and then sort of work their way over. But fundamentally, it doesn't matter. But I put it in the way that most character tables are put in, just by convention, so that, at the end result, we'll be able to very clearly see that we got the right answer without shuffling things around. One of the rules of the character tables is that they're always squared, so squares. So what I mean by that is the number of rows is always equal to the number of columns. So we have 4 classes, so that means we're going to have 4 rows, 4 irreducible representations. For now, I'm going to call these irreducible representations just generic names. We can't really give them Mulliken symbols yet, which is how because we need to know what the vectors are before we follow the rules for assigning the Mulliken symbols. Mulliken symbols is just a nomenclature that helps give you some key information about the irreducible representations, but we don't know what they are yet, so we can't do that. So I'm just giving them generic names: gamma 1, gamma 2, gamma 3, gamma 4. And the very first way to puzzle this out is we always know that the first irreducible representation is 1s across the board for every single character table. It's a totally symmetric representation, so we just fill that out. Next thing I like to do is do the rule where I know that the sum of the squares of the dimensionality, that's the characters underneath the identity, equals the order of the point group, or 10, the number of symmetry operations in the point group. So I know that going down, if I'm filling out this column here, I know that the sum of the squares, so 1 squared plus a squared plus b squared plus c squared, let's just call it a, b, c, has to equal 1 plus 2 plus 2 plus 5 equals 10, the order of the point group. And I got that from up here. There's 1 identity, 2, 2, and 5. And these numbers here are always going to be whole numbers. They're usually going to be 1s, 2s, and 3s. Very rarely in high symmetry point groups, you can have 4s and 5s, but basically 1s, 2s, and 3s. So you can stare at this for a while. And the only way to solve this is if you have 1 more 1 and 2 2s, because 1 squared plus 1 squared plus 2 squared plus 2 squared gives you 1 plus 1 plus 4 plus 4, which is equal to 10. So that's really nice because we can just fill this in here and it sort of gets us on the right track. Okay, so I'm just going to clear this out to give us some more space. At this point, there's a few options. It turns out that this one's going to be a little bit hard. I know the answer beforehand. These ones on the bottom here are going to be some non-integer values. So it's going to be a little tricky if we try to puzzle this out using orthogonality rules, which is the next step that we oftentimes do. But when we have a 1 here, this one's going to be pretty simple. So it's worth trying these orthogonality rules. And so let's think about how we would make this orthogonal. Basically what we have here, remember, we're looking for orthogonality means the dot products of every single vector. So gamma 1 dotted with gamma 2, has to be equal to 0, gamma 1 dotted with gamma 3 has to be equal to 0, gamma 2 gamma dotted with gamma 3, gamma 2 all dotted with gamma 4, all those have to be equal to 0, but it's normalized for, these dot products are normalized for the number of operations in the class. So what I mean by that is we write gamma 1, one of these operations we have to normalize by the, by one of these vectors we have to normalize by the number of operations in each class. So I'm writing, you know, in vector notation with these braces, or I guess brackets, writing out that, and I'm putting some space here purposefully because we're going to have some more room as we normalize things. But the dot product of this, when we don't know what these values are yet, I'm leaving blanks there. The dot product of this is going to have to be equal to 0, but again, we have to normalize for the number of operations. So we have one identity operation in that class, so we times by 1. We have 2 in the C5v class, so we have to times by 2. We have 2 in the C5 class, C5 squared class, and we have 5 in the sigma v class. And so if you stare at this for a while, you'll figure out that it has to be 1, 1, negative 1. If you're going to have a unique vector putting in here. This is the only place you can put a negative 1. And the reason is because there's 5 symmetry operations in this class, and the sum of these is also 5. There's 5 symmetry operations across these 3. So we have to put positives there, and then we kind of cancel it out with the negative 1 there. So if you see this dot product, it does indeed equal 0, right? This is going to simplify to 1, 2, 2, 5, dotted with our gamma 2, 1, 1, 1, negative 1, and that equals 0, because we have 1 times 1 is 1, plus 2 times 1 is 3, plus 2 times 1 is 5, plus 5 times negative 1 is negative 5, 5 plus negative 5 is 0. So we're good. And like I said, we could try to stare at this and come up with ways to do the same sort of orthogonality trick for gamma 3 and gamma 4. And the problem that we'll run into when we do that is that we don't have something easy like this. There's no integer values that are going to give us this same relationship where we sort of had, you know, the 5 canceling with the other 5. This is the only way you can kind of split this into equal parts. And so that tells us that, you know, there's going to be some non-integer values here, and it's going to get quite messy. So the best way is to start testing functions. So let's do that. And I'm going to draw us a pentagonal pyramid here, just so we can visualize. Okay, and I'm going to draw through that our z-axis. Remember, we always define, sorry, this should be going through the apex there. We always define our z-axis as containing the principal rotation axis. And then we're going to have our x-axis and our y-axis. I'm going to put coming out towards us. I can define this x-axis in any way, and it's a pentagon, so it's not going to be going through any bonds because these are all 72 degrees apart from one another. So it gets a little messy here, right? And so at this point, we go ahead and we see how various functions transform. So I always like to start out with the z-vector and see, what does the z-vector do? Well, if we do the identity on the z-vector, I know I'm going to get z. So we're imagining a little vector here, the z-vector. How is that going to change when I do identity? It doesn't do anything. What if I do a C5 on it? If I do a C5, I could do the C5, or I could do the C5 4 times. Those are the 2 symmetry operations in this class. If I do that on a z-vector, it's also going to go to z, because I'm spinning it like this. I'm spinning along the z, so it's not going to do anything. Same thing with the C5-2 or the C5-3. The 2, you can use either. The 2 classes, 2 operations in this class. And then the sigma v is also going to take a z to z. And so if you remember, that's because all the mirror planes, all 5 mirror planes, doesn't matter which one you choose, contain the z-axis. So if you're inside the mirror, nothing happens. So that tells us that z transforms as a totally symmetric representation. And guess what? That doesn't help us. It's fine, but it doesn't help us derive gamma 3 or gamma 4, which is what we're trying to do. So what we're going to do here is we're going to do x, and let's try x. So if we do x, we know an identity on x, the x vector takes x to x. So that's fine. All right, so now let's go and do a C5 operation. And now we have to think about, okay, we have an x vector. It's going to spin, depending on how we define it, clockwise or counterclockwise, 72 degrees. That's what C5 is, 360 divided by 5, 72. So we're doing a 75-degree rotation in one direction. That's going to turn into something messy. And it's actually going to turn into, for example, if we spin it this way, a combination of x and y. So that tells us, right, we started here with an x vector. That tells us that x and y are going to transform together. So I'm just going to write up here y goes to y, because we're going as a combination of x and y. And so we can write the identity matrix here. xy goes to xy. We can't describe how x transforms without also doing that in terms of y. And same thing, vice versa with y. Okay, so we take the trace of this matrix. Remember, the trace of the matrix is the sum across the diagonal. It's also called the character. That's why it's called character tables. So 1 plus 1, sum across the diagonals is 2. That's why we got a value of 2 right here. So that's tracing out just fine. But in order to figure out the matrix for C5, we have to use what's called the rotation matrix. It just comes from trigonometry. And what that is it's cosine theta across the main diagonal. And then we have a negative sine theta and a sine theta. And where the negative sign is depends upon whether it's a counterclockwise or clockwise rotation. Doesn't really matter how you define these things. So we're going to do a cosine, and we're rotating this by 144 degrees. And so I think we can, character tables will use either 144 degrees, or they'll use 2 pi over 5. If we want to do radians, let's do that. So we'll have 2 pi over 5. We're going to have, let's say, a negative sign over 2 pi over 5. Again, it doesn't really matter if there's a negative sign here or on this element. And then cosine 2 pi over 5, and then sine of 2 pi over 5. And so that's going to, you could do the matrix multiplication here, and I'm not going to write it out to show what it transforms to, but I'll say it in words because that's faster than writing out all this trigonometry. Basically, x, what this is saying is that x is going to transform into cosine 2 pi over 5 times x minus sine 2 pi over 5 times y, and y is going to transform into sine 2 pi over 5 times y plus cosine 2 pi over 5 times, sine 2 pi over 5 times x plus cosine 2 pi over 5 times y. Anyway, get the idea. And the key point here is that our trace, our character, is still the same rule. We just take the sum across the diagonal. We're getting kind of crazy non-integer values. But what this is telling us is that our character here is going to be cosine 2 pi over 5 plus cosine 2 pi over 5, which equals 2 cosine over 2 times cosine 2 pi over 5. So our character of C5 operation is 2 cosine 2 pi over 5. So that's what's actually going to go into our character table right here. things get complicated when you have C5s or C7s in your character table. Okay, and by the way, up here, chi just means character of. Is the notation I used. Chi of the identity operation was 2, because we had 1 plus 1. All right, so now we get to do the exact same thing for C5-2. And so it's going to look quite similar. Now we're doing a 144 rotation. Sorry, here was a 72-degree rotation. I think I said 144, but 2 pi over 5, that's in radians, is equal to 72 degrees. So here, though, we have to do 2 times that, so it's going to be 4 pi over 5 that we're rotating. That's 144 degrees in radians. So we have cosine 4 pi over 5. It's the exact same thing. Negative sign, but with 4 pi's instead of 2 pi's. Sine 4 pi, sorry, over 5, and cosine 5. And what do? We take the character of the matrix, sum across the diagonal, and we're going to get that the character here, C5 twice, is 2 cosine 4 pi over 5 plus cosine 4 pi over 5, which is 2 cosine 4 pi over 5. So that's our next part of our table. Last one. Let's see what happens here. We got a sigma v. Sigma v, what is that going to take x to? Well, we're going to have a mirror plane. And let's define the easiest mirror plane that we can. Let's define, if we redefine things, an easier way to redefine this, how I should have defined this to make my life simpler for this part, is actually if I define, so our z-axis has to be the principal rotation axis. Character table rules are designed this way, but x and y don't matter. So I'm going to define actually x, the x-axis. Sorry, this was confusing how I drew this so long. Let me just draw this going down. I want to define the x-axis is going through one of those bonds. And now the y-axis is going to be coming off sort of like this to be perpendicular. But if I define it as coming through one of those bonds, what's very nice is I know a mirror plane goes through one of those bonds, right? One of the 5 mirror planes. I can choose any of the 5 mirror planes. So now my x vector, it's right here, right? Now my x vector is in the mirror plane. And so that tells me that x goes to x. And the y vector is perpendicular to x, and it's looking at itself in the mirror. So it's going to go to, if I have a y vector in green here, it's going to go to the negative itself. It's going to go to negative y. So we get y goes to negative y. And so because we know x and y have to transform together for this irreducible representation, it's very easy. X and y, our 2 by 2 matrix, is going to look like this. 1, 0, 0, negative 1 equals x to negative y. And this one doesn't have any crazy trigonometry. I just put 1 plus negative 1. That's the character for our sigma v operation, which is equal to 0. So we get a 0 up here. And by the way, we can write here our function that x and y transform together. We put them in parentheses here to indicate that they transform as what we called gamma 3. All right, so at this point, it's a little tricky because we know that this gamma 4 is going to also be gnarly in the sense that it's going to have some cosines in there, because of the logic that we went through when we tried to apply the orthogonality theorem that we successfully used to derive gamma 2. And so at this point, what you have to do is either be pretty good at trigonometry and working out at orthogonality, or you're going to have to test other functions and hope that another common function that you can think of transforms as gamma 4. And so what we're going to do is we're going to do exactly that. We're going to test some different functions. And we know it's going to not, it's not going to be something like xz, because z isn't really going to help us, right? Because z is all ones. So that's just like multiplying everything by 1. So we want something complicated. So let's try, and it's not going to be something like yz, same thing. So let's try